Design of an electromagnet scissor truss deployment bridge. First designed during World War II, deployable bridges were invented to cross areas with inadequate infrastructure. Deployable bridges today are used in a variety of military and relief operations. Deployable bridges are lightweight bridges that are easily set up and taken down. The bridges are mostly used after natural disasters where transportation of supplies is urgently needed. But after such disasters, roads and bridges are closed or flooded, making it very hard to transport vehicles across. Different structural designs should be used to cross different spans because there are different stress dispersions. There are 5 main points that engineers designing the bridge have to remember in order to make a good deployable bridge. First, since the bridge has to be deployable without advanced knowledge of the span of the ditch or stream, it has to be able to be multiple lengths. Second, the construction material has to be readily available. Third, the bridge design has to be basic and repeatable, so that only that one piece has to be manufactured over and over again. Fourth, it has to be deployable, which means that it has to be lightweight for a few people to be able to carry it. And the fifth guideline is that the bridge has to be easily put up and taken down, so a simple design is needed. Kashmaka used a classic beam bridge design, laying down 2 750-pound planks made of a foam core with a carbon epoxy skin next to each other. 2 planks had to be moved in Kashmaka's experiment. The 2 treadways, each 4 meters long, were tested using 18 strain gauges, 9 on each, with 3 on the center line, each at a quarter span mark, and another 2 in line with those gauges a quarter meter away, perpendicular to the center line. 3 different trucks were run over the planks as measurements were taken, 2 wheeled vehicles and 1 with a track. The vertical deflection as the track truck rolled across at 18 kilometers per hour was taken, with the x-axis being the time and the y-axis being the strain. Interestingly, the result of the 2 treadways were not the same. This means that either vehicles were unevenly weighted or that one side was better built than the other. Either way, there was still a great amount of vertical deflection as the truck got closer to the center of the bridge. Augusturil and Abdullah both used the same design for their deployable bridges. It was a beam bridge that from the side was a solid trapezoid. It started at the ground, ramped up, was flat, then ramped down again. Where the slope angles changed, there were hinges so that the bridge could be folded into thirds. This allowed it to be transported in the back of a truck. The bridge was also very light. This is what it looked like from the cross-section. The outside, highlighted in red, was made of carbon fiber to support the top, highlighted in yellow, was aluminum. This beam bridge system works for short spans only because if there was too much weight added, the vertical deflection becomes too great and causes the bridge to fail. As you can see in the graph, where the y-axis, which is the independent variable in this case, is the load and the x-axis is the displacement in millimeters, already in the 6-meter bridge Augusturil designed was not even able to withstand more than 11.3 kilonewtons, which is equivalent to 1.15 tons. A longer span would not be viable. A deployable bridge should be able to hold a minimum of 30 tons. The yield limit for this bridge is 11.3 kilonewtons, because after that point the displacement changes drastically for every small increment of weight added. The article's other graph, deflection of the middle beam as the load is moved across the bridge, shows that the deflection in the center of the bridge is almost the height of the bridge itself. This is why beam bridges are not a good choice for longer spans, because they do not have reinforcements to keep them from bending under the load. All 3 journal articles used bridges that were short compared to the maximum possible span needed. Beam bridges do not work well for longer spans. Another design as suggested by Juan is a truss bridge with a scissor deployment. The design of Juan's bridge is very simple and is seen in other devices that use a pivot point. His concept was a scissor extension. The centers of the X's in the truss frame are on pivot points and shift to lay on top of one another when pressure is added from both ends. This causes each X to fold into one line, and the entire bridge is easily movable. Juan's bridge was strictly pedestrian and therefore did not have to carry as much weight and be as stiff as a vehicular bridge would have to be. This bridge also met all the deployable bridge criteria. Because it was able to scissor out and expand to any length, the scissor mechanism could be repeated multiple times and making it easy to manufacture because it is 2 truss members with a pivot point. It was made of hollow steel, which isn't that lightweight, but is available and is lighter than regular steel. The scissoring out is what makes it so easily deployable, and was the entire point of designing a bridge that way. Juan's bridge is deployed by having 2 scissor truss infrastructures. One infrastructure is used to be the top of a pulley to allow the actual bridge to slowly be dropped across the void. The purpose of this experiment is to come up with a new idea for a deployable bridge which is lightweight and durable. Before the proposed design can be explained, a general overview of where stress is on a truss bridge must be explained. The king posts are under compression and the truss members, the X's, are under tension. The top span is being compressed because of the vertical deflection as the load moves across, and the bottom span is under tension. The design proposed in this video is very unique. It will use electromagnetic magnets powered by the truck to expand the scissor truss bridge. The magnetic field is created when electrons spiral. By having one piece in the bridge spiraling one way and the opposite side spiraling the other way, 2 different magnetic poles are created, causing them to be attracted to one another. The king post will be a sleeve made of carbon fiber so that it is lightweight but still durable. 2 steel cylinders are able to telescope inside the sleeve. Those telescoping steel pieces would have wires coiled around them to create the electromagnet. The electromagnet would get its electricity from the car the same way a car is jump-started. When the magnet is turned on, the steel pieces are attracted to one another, causing them to come together inside the sleeve and shorten the king post, causing the truss pieces to scissor out. The only possible problem is that when the current is quickly released to the coils, the electromagnetic magnets may snap together too strongly and may rip the bridge by not giving it enough time to pivot. Therefore, like a dimmer switch in your house, a resistor will be in place to restrict the... Hypothetically, the best thing to use would be carbon fiber because it would create the lightest but most durable bridge. However, carbon fiber is very expensive. So instead, I'm going to use PVC pipes, which are plastic pipes, which are also lighter than metals, and are also very durable. After the bridge is designed and built, 2 tests will be done. One timing the speed it takes to deploy, and a second measuring the strain. The test that measures the time will have 2 variables. One where there is no variable resistor, and the second is using the variable resistor to deploy the bridge. Then a one-way ANOVA post-hoc Chaffee test with p-value less than 0.05 will be done, and it will be graphed with its averages plus or minus standard deviation. Strain gauges will be used to measure the stress exhibited when the magnets of the electromagnets are on, while they're on but have little power, and when they're off. Each of these groups will also have different weight loads: 50 kilograms, 100 kilograms, and 200 kilograms. 50 kilograms represents a person walking across the bridge because an average person is about 50 kilograms. And 100 kilograms would be a person with a backpack, and 200 kilograms is equivalent to either 2 people with backpacks or 4 people. Then, after the measurements are taken, a one-way ANOVA post-hoc Chaffee test with a p-value less than 0.05 will be done, and the averages will be graphed plus or minus standard deviation. For this project, I will need to buy the PVC pipe, steel rod, copper wire, jumper cables, wire splicer, a variable resistor, strain gauges, and sandbags. The PVC pipe is the outside of the king post and the truss members, with a steel rod telescoping in and out of it as the core of the electromagnet. and the copper wire is used to wrap around the steel rod to be the electromagnet. Jumper cables are used to transfer the electricity from a car to the electromagnet, along with the wire splicer and the variable resistor. For the measurements that need to be taken, the strain gauges will be attached to the bridge, and the sandbags will be placed on top of the bridge to create the weight, the load to make the stress and for it to be measured. Thank you for watching this video.